I'm Horacio, he's Alex. We are building Minter, which is a local-first and multi-device application using IPFS. First, Minter is a decentralized knowledge collaboration application powered by a knowledge graph. It's all local-first, and I wanted to explain, my main purpose here is to explain our, as a product side, our constraints, in order for us to build on top of that and try to achieve it with all the technology that we're gonna, actually Alex is gonna show you all. So I was gonna explain about why we're here, but our other co-founder, Gabo, just did a presentation before in the platforms and browsers track, which was very well explained about what hypertext is and all the things. I'm just gonna go very quick about it because I want Alex to talk more about the tech. I'm sure you are all more interested about the actual tech, not the product side of things. But we think that the public derivation process is in crisis. Like these are some of the examples. So we did a lot of research, and we found that I'm sorry, and we found that hypertext was the solution. And we found it 50 years ago from our founding fathers, which is Ted Nelson and Doug Engelbart. I don't know if no one knows those guys. Good, awesome. So essentially, we were betting that decentralized knowledge collaboration powered by a knowledge graph can spark human collaboration and can solve most of our challenging problems as humanity, right? So we built this application, and we actually package everything, or we try to explain or use everything via our Minter open hypertext document, which is just a fancy way of saying that it's a container of content of blocks that can be arranged hierarchically, and also anyone can create, edit, move them, even subtrees can be moved. And you can publish those documents, you can link between those documents, you can not only link to a particular document, but a subset or a part, even to a character level. So you can have very fine-grained detail, fine-grained links between Minter documents, which is quite powerful. So some of the challenges that from the product side we had to solve technically was, some of these are here. So we needed a way to have decentralized identity to empower human collaboration. We need some sort of version control system. We also wanted the product to work multi-device. And we needed the rich text to apply rich text capabilities on top of that. So people can express better the ideas using hypertext. So here's a high-level architecture. Right now we have a desktop application that looks something like this. You have the list view of documents and also the document view. You can see here that you can see some parts of one document that is reusing other parts of other documents. And here's also another view that you can not only see the base document, but also the extension, the discussions or the activity that is happening around that document. Here's a little video about how we, from the UI point of view, express this is part of that. This is that actual part of this other document. Here's also that also works multiple windows, so you don't have to be in the same window to show those things. And also, whenever you are referring to a document, this is how you do it. You copy right now a block ID, and then you're actually pasting a reference. You're not pasting the actual content, and it's all working as it is now. And also, you can do some cool interaction, like replying to a document, which is you just take a link to that document, you write something, which is hello from IPFS camp. And when you publish it, the original document knows that there's a link, there's a backlink to it. So people can start collaborating or discussing in a better way. We have also a link, a special schema. So if someone sends you a link via email, you can paste that link to our menu in the application. And we'll look for that document in the local database that we have in place, or maybe in the network. If we don't find it there, we just go to the network and look for it and render it. So local-first, like I said, it's everything. We are following these paradigms, started by the guys from Ink and Switch, which is pretty good. You can go to that URL if you're willing to learn more about that. And we believe that P2P enables local first, and we are betting on IPFS and libp2p to do that. So here's also a very narrow, or very like 100-foot view of the architecture of the application. We have the main process, which is built on Tari. We have a daemon, which is built on Go, and has all the IPFS and graph database and all the things inside. And then we have a web view. We have all the web views. We can have multiple web views that communicates with the daemon via a gRPC API. So this is all the magic that how we're using. And now, with that in mind, now I'm going to pass to Alex, so he'll show you how we're using IPFS.
Hi, everyone. Oh, I'm Alex. Really pleased to be here. Thank you. So we really believe that immutable nature of IPFS fits really well with our goals of longevity, history preservation, and content reuse. And let's dive a bit deeper into how we actually use IPFS. In some ways, it's a little bit unconventional because, for example, we don't use Kubo directly. We are kind of assembling our own IPFS node using the same lower-level components like bitswap, libp2p, and DHT. But we wouldn't use like even 10% of the functionality of Kubo, so we just don't embed it inside of our app. And first of all, we want to talk about decentralized identity, because if we talk about a decentralized app, we need to talk about identity and user's identity. And one of the most important properties we wanted to achieve with our identity model is that devices don't need to share any keys between themselves, between each other. So we don't want to compromise the whole user identity if you just lose a device and, I don't know, something happens, you lose access. We don't want to compromise your whole identity as a person on the network. So the way it works right now is that the identity begins with a cryptographic seed, similar to your crypto wallet, like Ethereum wallet or Bitcoin wallet. We encode that into mnemonic words, and that is the only part that you need to really keep secret. You need to keep it handy. You need to store it securely. And this is your key for your minter identity. And from that seed, we derive the account key pair, which is like a master key, from which represents you on the network. The public, it's actually a key pair rather, not a key. The public part of that key pair represents you as a user, as a minter user, and it becomes your user ID. And independently from that, devices create their own IDs totally at random, like you would normally do that when you create your IPFS node for the first time. You just generate a key. And then we essentially sign in a message with the account key saying that we want this device to represent this account. So you don't need to store that key. You just sign a message, and then you keep that as a proof that you have this cryptographic verifiable binding between these two keys. And then you use a device key as a peer ID on libp2p, and you do all of your actions on the network with that key. But you can always show that proof that you belong to that account. And you can create multiple devices like that independently. And the important thing is that they're disposable. If you lose the device, you can always revoke access by just signing another message with this account key. So you can just introduce the mnemonic words again in other device, and you can revoke some other device. And you just say, like, don't pay attention to this device anymore. Doesn't belong to me. So if we talk about application, we need to talk about mutable content, because we want documents, we want to change them, and well, we need mutable content on an immutable network. So traditionally and conventionally, this is done on IPFS by having a mutable pointer like an IPNS name, right? So you have some piece of data, you want to create a new, you want to update it, you create a new piece of data, and you flip the pointer to the new CID. And this is a bit wasteful if you want to keep all of the history forever like we do, because you have to keep every version of that state in its entirety. And things like HAMT, things like UnixFS chunking can help that and improve the situation for large files or directories or videos. But for small pieces of data, this is still kind of wasteful, because you wouldn't make smaller blocks, because sometimes CID can get larger than the content itself. And this specific example is from the IPFS website. And this is a little bit extreme, because you have blocks that are super small. And like having mutable pointer for these blocks and having to keep all this data around could accumulate, and you would have more CIDs than content, actually, if you really hash them. You could use, of course, the raw CID to encode them, to embed that. But still, the more important thing with this approach with mutable pointers, where we think that it falls short, is that it's inherently not multi-device, because you have to have the key for IPNS record to update it, and we don't want to share any keys, as we said. And when you're talking about trees like we do with Minter documents, they are hierarchical trees, and we want to collaborate on them. This gets especially hard. And what's worth mentioning is that when we talk about multi-device and interacting with the same document from multiple devices, it also applies to collaboration. Because from the standpoint of history, of preserving history, it doesn't really matter if it's your own device or if it's someone else's device that does the change. So we could have a use case like, so imagine if an Alice publishes a hierarchical document, and then we have Bob who moves a content block to another place. And at the same time, we have concurrently Carol moving the same block to another place. Having those snapshots of those documents is just not enough for making like sensible outcome if you want to merge those together. It's really hard if we don't add some additional information. And it's hard for having these mutable pointers that you need to sign messages to keep the pointer alive and to update it. So we don't want to share keys between devices, and we don't want to share them between untrusted peers either. So this is where we think that IPNS falls short in this use case. And interestingly enough, I discovered this video recently browsing IPFS research websites. So it seems like there are folks in the community who thinks the same, that mutable pointers are not enough for distributed application. And we strongly believe that CRDTs are the solution to achieve what we want. And before there was a panel, I don't know how many of you were present here on the panel, they were discussing CRDTs and well, some of the challenges that we have with CRDTs right now, but we're going to talk a little bit about that because we think that they can be made a lot more simpler than they're currently trying to be made, especially if we don't talk about real-time use case, like real-time collaboration. So in our case, we talk about asynchronous collaboration. And essentially what we want is some kind of a version control system, similar like to Git, that we all know, I guess. And when we talk about version control system, we need to think about whether we store snapshots of objects or changes to objects. And we've seen the limitations of storing snapshots with IPFS. So let's talk about storing changes, because this is what we ended up doing at Minter. So what we do is we store changes to the data instead of the snapshots. And the way we do it is that we create a mutable object by declaring what we call a permanode. We borrowed this name actually from another project called perkeep. It's unrelated to IPFS, but also uses content addressability for many things. And essentially, it's a IPLD object that declares a mutable object in the Minter world. What it is, when it was created, who's the owner of that object, and we try to add this @type thing to all of our IPLD objects that we create because we think IPLDs are not sufficiently self-descriptive. We wanted to add some additional information that seeing a piece of data, you know without context, or at least you can guess what it represents. And this idea is also like similar to what Semantic Web Linked Data Initiative is doing, JSON-LD and stuff like that, if you're familiar with that. So the CID of that permanode becomes the ID of the object, and then you apply changes to that permanode. And change says what changed and who changed it. And then you add more changes that point to previous ones, forming a hash chain of events, not very different from a change of Git commits or even a blockchain, although we don't talk about consensus here. We don't need blockchain for what we do. And those arrows are actually IPLD links. And on top of that, we have our own syncing protocol to actually discover what the version of the object is. It's a rather dumb protocol right now, but there are ways to improve it. And, well, we are not the only ones who are taking this approach for mutable data on IPFS. Projects like Textile, Ceramic, OrbitDB, Berti, Query, rest in peace, and others took a similar route to representing mutable data. So you could have, they all based on the idea of an append-only log. You would have Alice's log, and then you would have those messages and chained with these links. And you could replicate this to another machine pretty easily, and Bob could have his own log of messages, and you can even do something useful by combining those two together, depending on what you actually put in there. But essentially, it's just like a one timeline of events for a user. And if we talk about version control system, we want to sometimes go back in time, create different perspective on some things. So we want some kind of branching, and one timeline per user is like really limiting in this aspect. So what we ended up doing is we ditched the rigid linear log structure, and instead we let changes to those objects to form arbitrary DAGs. We all know what the DAG is. I'm not going to dig into that. So what's inside of those changes? And we landed on this rather simplistic data model for our CRDT. We essentially say that a Minter object is kind of a namespace, a scope for arbitrary entities that have identifiers that don't have to be large identifiers. They only need to be unique within the namespace of the object. So we just use 64-bit random numbers in there. And those identifiers, those entities identified with these IDs have arbitrary attribute value pairs. And if you've ever worked with a triple stored graph database or something like that, or you're familiar with RDF, you would find this familiar. And we also add in there a timestamp. We use hybrid logical clock for that. I'm going to take a look. It sounds a lot more crazy than what it is. And we also add origin, which is the device ID, the shortened device ID with about who did this change, who added this attribute. So those triples that we also call datums internally, inspired by the datomic database, graph database. So that simple data model is simple to reason about. You can decompose pretty much any piece of information, any piece of data into these triples, entity, attribute, and value. You can even express links between those entities. So essentially, it's kind of a little graph of data. And I think that a graph is like an ultimate CRDT, especially if you don't remove anything. You only add nodes, you only add edges, so you don't have any conflicts when you insert, at least. And when you read, you can do a bunch of different tricks to represent a lot of different data types. And a little bit about hybrid logical clock is just a combined wall clock plus a counter, which you increment if your wall clock ever gets back in time. So if you synchronize with NTP or anything, or if you receive an event that's from future time than your current wall clock, you get incrementing this counter, and you always produce a timestamp that is in the future from all the other events that happened before. So summarizing, we have the permanode, we have the changes. There are those triples or datums inside of each change. There are IPLD links between those changes, and those links express causality of events. So a newer change, changes that are linked in the new change are always guaranteed to have happened before that new change. So having this causality is really important when you implement the CRDT. And essentially, the state of the object is defined by a set of those changes. So you get all the changes, you put it to another device, and you have the same state of the object. But we need something to identify the version of an object and to reference different versions of things, because we want to be able to address things in older versions of the documents and stuff like that. So we only need to really identify the leaf nodes in this DAG, which is essentially like a root of a Merkle DAG. But we treat as a root the permanode in our case. And you can also mix those. So in this case, C3, the change C3, the leaf node, is a version, but C1 and C2 are also versions, and the combination of C1 and C2 is a different version. And those two commute. It doesn't matter which one goes first. The state essentially is going to be the same. So having all this information, the causal DAG of changes, atomic attributes, and in these attribute value pairs, and logical clocks, we can implement different data types. And we don't have time to dig into the details of each of these data types. And we are using well-known CRDT algorithms, adjusting them to this rather simplistic data model. So we use RGA or causal tree algorithm for lists. We use last writer win semantics for simple registers when you need only the last values. But the interesting one here is the tree, because we want those trees. We want to be able to move a block to a different place, and even subtrees of those blocks. But we want to merge those together and generate a sensible outcome when we merge different perspectives. And gladly, unfortunately, we didn't have to come up with the algorithms ourselves. So huge shout out to Martin Kleppman and his team for all the research that they're doing in the field of CRDTs. And this particular paper describes the algorithm that allows you to do tree manipulation, resolving conflicts, moving subtrees. And what's important here is that we want to preserve the position. So it's a combination of actually a last writer wins CRDT plus a list CRDT. So we move something to another place, but we want that node to be at a specific position in the sublist. So we can combine those different CRDTs to represent these manipulations. And we store, going back to how we store the accounts and these bindings between account and devices, we store them in a similar way. We have a separate object that represents your user account. You store there your name, your alias, your bio, whatever you want to store there. And also you store there these cryptographic bindings between devices and accounts. And we have some more interesting things that we don't have time to talk about right now. So we do like a lot of stuff. We have our own block store backed by CRDT, by SQLite. We have a special draft mode. So when you edit the document, you don't need to constantly updating the immutable change. You can write a document in multiple settings. You can get back to it later before you publish it. And then when you're ready to publish, you click. And then when change is created and it gets signed at this time. We index IPLD links between changes in a separate index. So we can query, like doing recursive SQL queries, we can query the ancestry relationship between those changes so we can know whether one change is ancestor of another one. We have index for backlinks, so the thing that was shown on the video where you link something and then you can see in the other document that it was linked in the other document. We have named versions, which is like it's kind of like a named branch in Git. You give a name to some version of something and then you can keep it, like referring to it by a name. We also do gRPC over libp2p, which I think some projects out there are also doing. It's pretty fun. And well, we think that local-first, CRDT, and peer-to-peer are things that really belong together, fit very well, and essentially our future of local computing. I really believe that you don't need consensus for many applications. There are many, many valid use cases that you can build with local-first paradigm, and many useful applications could be built with that. So you might ask, what about private data? And the answer is that we left it for future right now, focusing on open use cases, open deliberation. And the main reason of that, and this is also a funny example, excerpt from the IPFS website, saying that encryption isn't bulletproof. And the state of art of private data right now on IPFS is encrypting things. But personally, I'm not feeling comfortable putting my sensitive data, encrypting it on a public, and leaving it on a public network, because right now encryption might seem bulletproof, but we don't know what's going to happen in future. And as of 3 days ago, we made the repository public on the call that we had. So you can visit us at GitHub, minter.team/minter, and you could also join our Discord community that we have linked here. So with that, thank you very much. Thank you for having us. That's it. Thank you.